Thank you for all to giving me a chance to share my experience regarding commissioning of medical LINAC. We have recently installed a linear accelerator in our center, and we are planning to have a few other machines of radiotherapy and the nuclear medicine in future. Basically, my name is Faisal Ali, and I did my master's from Pyas, Islamabad in medical physics. Right now, I'm working as a senior medical physicist at the Nuclear Institute of Medicine and Radiotherapy, Jamshoro, Pakistan. First of all, this is a disclaimer. This presentation is for the academic purpose only, and the authors do not have any conflicts of interest. My presentation layout is the brief introduction of the institute. I will discuss in one slide about my institute, the machine model we have, the dosimetric equipment we have, treatment planning system requirement, beam data for TPS beam modeling, and data processing for TPS, dosimetric leaf gap measurement, and beam data validation. Can you all hear me properly?
Yeah, I can. I think everyone can hear you.
If anybody has issues, kindly let us know.
Sure.
Should we proceed?
Yeah, yes, you can proceed now.
Okay. Right now we have a linear accelerator. We have just installed in January, and Cobalt 60 machine we had earlier two. One we dismantled and one we have in functional. Then we have CT simulator, conventional simulator as well, mold room. In future, we are planning for halcyon and brachytherapy. Inshallah, we will have a spec and a spec seat to be installed.
Faisal, we can't hear you.
Hello.
Yes, I can hear you now. There is a distortion before, but now I can hear you.
May I share the screen again?
Yes, sure.
Okay. We have a linear accelerator of a variant and a D2300 CD. It was planned in 2015-16, but due to a bunker issue, it is installed in 2020. Oh, sorry, 21. So the machine is capable of having 6 MV photon beam, 15 MV photon beam with electron energies from 6 to 22. And 120 millennium MLCs, an electronic portal imaging device. When I was working on these PPT slides, I was trying to have a practical situation where what we encountered during the commissioning. Dosimetric system, we have MP3 3D water phantom with the dimensions 694, 596, and 503. Unidose electrometer of PTW company and their software, Mephisto software for the acquisition. Ionization chambers we had 10.3D type. We had 2 chambers, a dosimetric diode, 2 SAMI flux. We had 2 former chambers also. We had 2, and Marcus chamber we have 1. So these all the chambers we have used in during the commissioning of the linear accelerator. These are the few details of the ionization chambers. You may have already know about this. Those who are working with the radiation facility, they are already familiar to it. So the other operating voltages and the reference points. Reference points is important when we are using the chambers, because we need to move the chamber at the reference point. So these values are critical during the acquisition. These are the chambers. For example, we have holders of the chambers, thimbles. This is semi-flux, former chamber, dosimetric diode chamber, pinpoint chamber, and we have Marcus chamber. Treatment planning system requirement. During the commissioning of the process, you need to first evaluate your beam configuration requirement, what this treatment planning system requirement is. So if you go to the beam configuration, you will see your machine, you will see your energies, and you will also see algorithms you have incorporated in this machine. For example, we had AAA, we have Accuracy, and then we have portal dosimetry, and photon optimizer. Similarly, these all algorithms will also be available in the next photon energy. We have 15x. So we are similar, all four algorithms are there. Then or 6 electron and 9 electron MeV, 12 MeV electron, 15 MeV electron, 18 MeV electron, 12 MeV electron. This snap I've taken after the modeling of the treatment planning system. So when you will see before commissioning, you will have only these numbers, AAA minus -161, whatever the version you have. So you need to add all the commission data into these modules according to these algorithms according to the requirement. We will discuss one by one. So how we did commission. If we go into the 6 MV photon beam, and if we look for the AAA 161 algorithm, you will have a few, when you click on this, you will have a few other parameters, required parameters. For example, journal parameters. Few parameters will also automatically available by the system, but few you need to put into. For example, how many number of profiles you are going to take, what is the depth of the first profile, second profile, third profile, fourth and the fifth profile. You will going to take the data, you have to mention all these values here. You also mentioned that other qualifier values, for example, source axis distance 100 centimeter, source to phantom distance, for example, 100 centimeter, largest open beam in X direction, 40 by 40. This is the journal parameters you need to incorporate in this algorithm. After that, if you move further to the other parameters, then after the general parameters, you will fulfill the parameters. In parameters, you will incorporate few values. For example, absolute dose reference field size, you will say, for example, in millimeter, it would be 100. Absolute dose calibration source phantom distance, 1000 in millimeter. Absolute dose calibration depth is 100 centimeter or 100 millimeter, because we uses the calibration 10 centimeter. Somebody can use 5 centimeter as well. And the reference dose at calibration depth, that is 0.6692, the value we find from the data we incorporated in reference MUs and the calibration depth. And these and the machine model and the collimators type, you have to provide this data to the system. After that, when you provided the general parameters and parameters, if you are going to configure, for example, you are looking for the open field configuration, you need to add 4 specific data files into the algorithm. It would be measured diagonal profiles, measured profiles, measured depth doses, and output factors. These all the name headings below will system will automatically calculate on the basis of the 4 provided files: diagonal profiles, simple profiles, depth doses, and output factors. So when you want to configure 6 MV photon, one algorithm, for example, AAA, you need to add channel parameters, and for open field configuration, you need to add measure diagonal profiles, measure depth doses, and measure the output factors. Now, if you have a physical wedges, obviously, if you're using the 6 MV beam, you would have a physical wedges also. And similarly, in that same window, in the same algorithm, you would have an option of standard wedge of 15. Again, for wedge configuration, again, you need 4 different files. For example, you will first add wedge parameters, and wedge parameters are mentioned here also. You have to mention the wedge length, wedge width, wedge material, and wedge orientation. This is very important. Whatever orientation you choose for the wedge, use it throughout the data. Use the same orientation. Then wedge angle, then wedge reference rules at calibration depth, and a few other informations you need to provide in the wedge parameters. After the wedge parameters, you need to add few data files to the wedge add-on. For example, wedge depth doses, wedge profiles, wedge longitudinal profiles, and output factors. Again, in the wedge configuration, you need 4 data files to incorporate, and wedge parameters you have to provide in order to configure wedge 15. Similarly for wedge 30, similarly for wedge 45, and similarly for wedge 60. And if you are switching from AAA to Accurus, so in Accurus you don't need to configure. For example, we didn't configure wedges in Accurus. We only configure open field in Accurus. So it's up to you whether how you are approaching the system. Before going towards the other side, definition of a small field we need to address. We will going to take data in 2x2 2x2 field, 3x3, and a 4x4, and they are the small fields. So in small fields, we need to use different chambers. So I've just mentioned a slide. So what type of a field will be considered as a small field? There are 3 conditions. There is a loss of lateral charge particle equilibrium on the beam axis. There's a partial occlusion of the primary photon source by the collimating devices on the beam axis. The size of the detector is similar or large compared to the beam dimensions. If your field falls in this category, it would be considered as a small, and then we need to use different chambers as compared to the field 5x5, 8x8, or 10x10 and above. So we will discuss now the 6 MV photon beam. Open field percentage depth dose. The system required the percentage depth doses, or in open field percentage depth doses. So the setup we had, the proper level water phantom is very important. Select proper holder and thimble for ion chamber. SSD should be 100 centimeter. You have to use 2 ion chambers, reference and main. We use semi-flex for field sizes above 4x4, and diode and pinpoint for small field sizes 2x2 to 4x4. Select proper chamber step size in the build-up region, and set parameters on the software according to the PDD. For example, we are getting the PDD of 6x6. We need to mention energy and something like this. Field sizes, what by default is required: 2x2, 3x3, 4x4, 6x6, 8x8, 10, 12, 15, 20, 30, and 40. You can use different field sizes also, but this is the minimum you have to incorporate into the system. We were new in the commissioning. We had issues with the symmetry of the beams. Those who are very new with the dosimetric system, so you can cross-check your system. Once your setups for the PDD, acquired PDDs of the photon of reference field size and evaluate Dmax value, it must be within defined limit. To check whether your chamber is properly aligned, your phantom is properly aligned or not. Acquired in-plane and across-plane beam profiles of 10x10 and evaluate the central axis difference. Acquire profiles of 10 by 10. This is my suggestion, that acquire profile of 10 by 10 centimeters square and a bigger size 25 by 20 for multiple depths, for example 10 centimeter and 30 centimeter, and evaluate symmetry that should be less than 2%. We had issues with the symmetry in larger field size because of setup. So later on we realized if you install a setup, then you have to verify that your symmetry should be within 2% throughout all the sizes. So it's good to have a random check in the first to before the acquisition of the data. If you find your setup is good, everything is okay, you can proceed for the data acquisition. Open field percent depth doses. We acquired the PDDs of almost all sizes I've mentioned earlier, and this is the acquired PDDs we acquired for the 6 MV photon beam. Then open field profiles. For open field profiles, setup is very much similar to the PDD. Proper level for phantom, again, leveling of phantom is very important. Select proper holder and thimble for ion chamber. SSD again is 100 centimeter. Use 2 ion chambers reference main, again semi-flex and diode pinpoint for small fields. Select proper chamber step size, maybe uniform. We use 2 mm step sizes throughout. Set parameters on the software according to the profile, because whatever parameter you choose, it will be incorporated into the text file, into the file. So it would be difficult to change if once you get the data. So it's good to have properly proper parameters on the software. What you need to get, 5 at least profiles at Dmax at 50 mm, 100 mm, 200 and 300. So you have to fill complete this box for the open field profiles.
अच्छा, वालेकुम अस्सलाम। अच्छा, मैंने कहा था कि एक आधे दिन उधर चक्कर लगानी है सैनिटरी की।
Open field profiles, we have this is the total open field for profiles for the 6 MV photon beam. That will be later we will discuss to incorporate in the system.
We have a question here for cross check. Can I ask now?
Yeah, I have read it. I'll answer it.
Okay.
Absolute dosimetry is important. I guess we did not perform prior to commissioning, but it's good to perform prior to commissioning. But we had issues with the phantom itself. We had multiple issues with phantom rods, their leveling. So we acquired a complete set of data almost, and it was very within range up to 20 to 25 by 25 field sizes, and later on the symmetry goes out of range and the system rejected those files. Then we fixed the phantom from the engineers. Then after that we took again data. So recheck is simply because if somebody who is working with the phantom, he don't need to recheck, or she don't need to recheck, because he has the experience how to set the phantom. But for somebody, if somebody is new, it's good to check the symmetry on both on the smaller field size, on the larger field size. It will give an idea that your phantom and the setup is properly proper, or you have to check it again. Just as a cross, not mandatory. May I proceed for the slides?
Yes, sure, please.
Then we have open field diagonal profiles. For diagonal profiles, again, level phantom is mandatory, but we have to center the phantom to the corner if of our phantom size dimension is smaller. We had a smaller dimension, for example, like 60 by 50 by 50. So for this acquisition, we moved the phantom to the one corner in the gap, centimeter gap for lateral scatter lateral scatter charge, and we acquired data at that particular setup. SSD gain was 100 centimeter. Two ion chambers was used. You just need to open 40 by 40, and you need to find out 5 these diagonal profiles, and properly you should mention the parameters on the Manifesto software, because it will be incorporated in the file. These are the diagonal profiles we required: 40 by 40 by 40, 16 mm, 50 mm, 100 mm, 200 mm, and 100 mm. Open field output factors. Again, for the output factor, your phantom should be properly leveled, chamber properly choose. You can use former chamber or a semi-flex. We use semi-flex for it, and we uses the electrometer, unidos, and SSD 100 centimeter calibration or acquisition depth for output factors. You can use 5 centimeter, you can use 10 centimeters. The rest of the values will be according to this depth. Normalization should be at reference field size, that would be 10 by 10 centimeters square. Incorporated correction factors in small field sizes. In small field sizes, we have incorporated as correction factors as advised by the Dr. Atiya Gul from Ahmedabad. This was the table. I have also mentioned the report in the last of the slide. For whatever chamber you are choosing, and if you have a small field sizes, you can incorporate correction factors from this table. And there would be a slight difference in the values after the application of the correction factor. When you will provide the system your output factors, your system will show table in this format. I'm going to provide data in this format, but the system will show you the output factors in this format. For example, field size in this direction and the field size in this direction, and you have multiple cells of the values. System will ask you for output factors, you need to put a text file. So when you're taking the output factors, it would be in the Excel sheet. After the manipulation, whatever normalization procedure you want to perform, and when it is finalized, you have to convert that particular sheet's data of output factors into the text file, because the system will require a text file for the output factors. When you're working on your, when you will work on your Excel sheet, you can directly plot your output factors to evaluate whether any typo mistakes or something like this. So your output factors curves, your graphs would be like this. Wedge 15, 6 GMV Photon beam. For wedge acquisition, again, you need to get the percentage depth doses. For field sizes, now field sizes will be according to the wedge dimensions. So 4 by 4, 6 by 6, 10 by 10, you can add 8 by 8, you can add 12 by 12, 15 by 15, 20 by 20, 30 by 30, and 30 by 40, according to the wedge dimension. As the dimension changes, your 30 by 40, and this will also be changed according to the wedge dimension. So again, setup will be very much similar to that, and use wedge in one direction throughout, either right or either left, or whatever you choose, you must be consistent with it. The second step, for example, again, the percentage depth doses you will have, I have shown, we have acquired these EDDs for wedge 15. Then wedge profiles. Again, there would be a cross beam profiles, because normally in cross profiles, the phantom is in bigger dimensions, so it is easy to take the data in cross plane. So again, for wedge profiles, you need to use 2 ion chambers. Similar proper chamber step size should be there. Properly you input proper parameters on the software, and again use the wedge in 1 dimension. Again, we need to have profiles, 5 profiles for each field size. For wedge 15, for example, D max 50, 100, 200, and 300 mm. So when you when you'll get all the profiles, you will have this sort of a complete picture of wedge profiles. In open beam, we took the diagonal profiles, whereas in the wedge field, we need to have longitudinal profiles. A longitudinal profile means the profile in a non-wedge direction. So it's up to you if you are using the direction of wedge as right. So either you can take your longitudinal profiles in plane, or either you can rotate your collimator and you can do it in the cross plane direction also, but that would be longitudinal profile. Whatever you look that would be easy for you, you can do it. You can do it in plane, you can do it in cross plane. If you are doing it in cross plane, you just need to rotate the collimator. Okay, again, similar, I have a few things are similar to the setup, and in plane and a cross plane, both directions can be used for the acquisition. And for 40 by 30 field size only, you need to acquire longitudinal profiles at Tmax 50, 100, 200, and 300. We acquired 5, for example, 16 mm, 50 mm, 100 mm, 200 mm, and 300 mm. It was a half beam profiles you can get, because it is a big dimension as compared to the size of the field is greater as compared to the size of the phantom. So you can incorporate in the half beam profiles format also. System will accept this. Wedge field output factors is similar to the as we discussed in the open fields, but few field sizes will not be incorporated because of the dimension of the wedge. And again, we can use hemiflex former chamber, SSG 100 centimeter, calibration can be 10 centimeter or 5 centimeter. You should normalize at 10 by 10 centimeter. If you consider any small field, you can apply correction factor also. Again, field wedge field output factors would come would be like this in the system, and by if you're using the plot to figure out whether is there any mistake or not, you can directly plot on the Excel sheet. So we have discussed till now this 6 MV open beam and wedge 15 6 MV. So all the wedges are similar to the what we have discussed. The procedure will be same for all open beams. The procedure will be same whether you are commissioning 6 MV or 15 MV, or wedge with 6 MV or wedge with 15 MV. The procedure will be similar. So we have discussed only one steps of 6 MV in open and in wedge. Then the second procedure is the 6 MV electron beam. The procedure of 6 MV electron beam and 12, 9, 15, 18, and 22 will be similar. So we will discuss only this. So properly leveled water phantom should be there. The proper holder and thimble of ion chamber. SSD should be 100 centimeter. Use 2 ion chambers, reference and main. Semiflex, we use to select proper chamber step size and build-up region, for example. So set parameters on the Mephisto according to the PDD, according to your steps. Ion chamber's speed can also modify to reduce water movement. 40 by 40 centimeter is a wide open beam PDD required for all energies. We have to get this size PDD for this side for all energies. Applicators are smaller than this size, so we need to override the accessories in the service mode in order to get the PDD at for 6 MeV electron beam at 40 by 40. So 6 MeV 40 by 40, we have 9, 12, 15, 18, and 20. All energies 40 by 40 wide open PDDs required. and you would have a similar picture like this. After the PDD, you need to acquire the wide open field profiles, and that would be in air. So again, water should be leveled properly. Select proper holder and thimble for ion chamber. SSD should be 95 centimeter in air. So it's better to move your chamber with when it is filled with water, and set your SSD at 95 centimeter. And when you think that your chamber is properly set up, so now you can remove the water from the phantom and you can acquire these open field profiles. Against two semi-fixed chambers and 40 by 40 with a wide open beam. So need a profile. So accessory must be override. So sorry for this. This is not PDD. This is profile. So profiles will be look like this: 6, 40 by 40, 40 by 40, 9, 12, 40 by 40, 15, 40 by 40, 18, 40 by 40, and 22, 40 by 40. So these are the open beam profiles at 95 centimeter. After these two, you need to get PDDs with all applicators for all energies. For example, if you have 5 applicators and 6 energies, so you would have 30 PDDs with applicators. So setup is quite similar as previously discussed in 6 MeV electron. But only one thing different is where you will not going to override the accessory. You will use the proper applicator. For example, for 6 MeV, we use 6 by 6 applicator, 10 by 10, 15 by 50, 20 by 20, 25 by 22. Because energy is similar, so PDDs are quite similar and superimposed on each other. Similarly, you will get for 9 MeV, 12 MeV, 15 MeV, 16 MeV, and 22 MeV. Data processing for TPS. Acquired data is in MCC file. System required data in ASCII and text file format.
Are you good? Yes.
Can you see the slide?
Yes, I can.
Okay, thank you. Everybody can hear me?
Yeah, I can hear.
Okay, data processing for TPS. What we will require data that would be in another file format, and what system needs data that will be another file format. So acquired data will be in the MCC file, whereas system required data in American Standard of Code of Information Interchange ASCII file and text file format for output factors. So if you are configuring AAA and Accuracy, 6 MB photon beam for 6 MB photon beam, including wedge data also. So you need to combine all PDDs in a single file for open field. Similarly, for in another step for the wedge, and convert it using Mephisto software program to ASCII file format. So whatever dosimetric system you have, you can do this. Combine all profiles in a single MCC file and convert it using Mephisto software program to ASCII file format. So you converted all PDDs, combine and converted. You combine all profiles and converted into ASCII format. Again, similarly, you would have diagonal profiles, and again combine them and convert it into ASCII file format. Whereas output factors, you need to normalize on 10 by 10 reference field side and convert this table into the text file format that I've already mentioned. For electron, convert all files in including wide open beam profiles, profile in air, and PDDs with the applicator into ASCII format. In electron, you don't need to combine all files. Those files will be separately converted into ASCII format. During this conversion, system will ask for reference depth and dose value at reference depth for each PDD. When you will convert your PDD into ASCII format, the system required these two values, Z reference and the dose value at Z reference. You need to give this. You can get these values from the PDD and normalize them at the reference applicator. I have mentioned how we've done this. 6 MeV applicator, 10 by 10, 15 by 15, 20 by 20, and then 40 by 40. These are the values at the reference depth, and these are the normalized at the 15 by 15 applicator. Few people normalize them for 6 by 6, 10 by 10, 15 by 15 at 10 by 10 applicator, and above at 15 by 15 applicator. So whatever, we use only normalization at 15 by 15 applicator for smaller and the larger applicators. Dosimetric leaf gap measurement. For dosimetric leaf gap measurement, you can run directly DICOM plans from the TPS, or you can directly run MLC plans of the specific configuration from the computer, the machine computer, using pen drive or CD, whatever mode you choose. We use a .mlc plan will 2, 3, 4, 6, 10, 14, 16, and 20 mm MLC gap movement plan, and transmission A bank and the transmission B bank plan. Use chambers at the calibration depth 10 centimeter or 5 centimeter, and the SSD must be 100 centimeter. Enable integrated charge option in the electrometer because your gap will move gradually. So you need to collect the charge throughout that movement. So integrated charge option should be enabled. After collecting the reading for all needed plans, you just perform some basic calculations to get DLG values and the transmission factor values. So if you're going to, you can run these DICOM plans from the system, or you can directly use this MLC plan from the machine's computer. So this is the basic calculation you can perform. We found this document from the variant. So there are other methods of dosimetric leaf gap measurement also. You can use any of that in order to get the DLG measurements. So these are the steps. For example, in first step, you will calculate contribution of the average MLC leaf transmission to the gap. For each gap, then the contribution of the transmission to gap rating is defined as. So it's very simple. You just need to get the values, charge values for each plan, and you need to prepare a small Excel sheet, and you can get your transmission factor and your DLG values from this. Then the last is the beam data validation. Once you incorporated the system, when you configure the system, you need to validate your data, whether what system is providing you what value at the treatment planning system. You have to verify that this value should meet with the practical value at the phantom or at the machine. So for the beam validation, we use multiple plans over the phantom. And for example, different field sizes like 7 by 7, 10 by 10, 14 by 14 at various depths. So we have, I've checked the multiple dose point values at different depths for different field sizes. For open fields, these are for open fields, for EDW, for wedge fields, physical wedge fields, and all these. And those values or the dose difference should be within 3%. Our difference was within 2%, but it may be within 3%, it is okay. You don't need to configure the enhanced dynamic wedges. It will be automatically incorporated in the system. So you just need to provide the open field data to the EDW module, and system will automatically incorporate or configure the enhanced dynamic wedges. For photons, you just need to configure separately 6 MV, for example, open beam and all physical wedges for photon energies. And the EDW will automatically incorporate it and will require the open beam data. Similarly, we use arc plans also to check the absolute dose as a central point on the Octavius phantom. We use also Octavius for the absolute dose check. So you can also use this. And we also use a multiple MLC plan to verify whether the treatment planning system's value is actually meeting with the value we are calculating on the machine, but it is with a good agreement. Similarly, for electrons, we just need verified few data points on the reference depth, and it was within 4.5% as required. For you can read these. There might be other documents too, but we use this absorb TRS 398 for absolute dosimetry, technical reports of 483 for small field in external beam radiotherapy, and we also use the variant beam data guides that will be quite helpful in the acquisition of the data. So this is what I have. You can whatever question you have, you can ask.
Thank you very much, Faisal, for this detailed and comprehensive review on commissioning linear accelerator. I urge all participants to please unmute your mic and ask questions if you have.
I'm Talat from Perth. Yes, it's quite useful. We have also the same planning system. Do you have IMRT and BMAT as well?
So we have 2 licenses of IMRT, but we don't have license of VMAT right now.
Okay.
But still, we are not using the IMRT because our total staff is very much new,
Okay.
including doctors. So we are already running with. We have spent 6 months on few 3D CRT, and still we are having that fixed RT mode on the machine also. But we are trying to incorporate the total planning with the system.
Yeah, that's fine. That's what I was just thinking about, because that's why you didn't did the end-to-end testing based on the DG 128, 218 something.
398 and 483, sir.
No. I'm saying for IMRT implementation, there's a separate report for specially which is related
Yes, sir.
to
Yes,
the
sir.
Machine
Exactly.
characterization and also your TPS characterization. So
Yes, sir, exactly. I have an idea that I have to go through the various checks in order to start IMRT.
yeah.
So with time, I'm doing on that, making few plans and delivering them with with the leisure time. That is there any ambiguity I can find out and can figure out before the starting of IMRT?
That's fair enough. Other thing, when you are measuring your data, when you normally change the field size, but especially for photons, you're using IBA phantoms, isn't it?
No, sir. We have the conversion from MCC.
No. The phantom, the 3D phantom I'm talking about.
I don't understand the question, sir.
I think he's asking about the water phantom you have.
So we have a 3D water phantom, simple.
Which one? Which company?
Sir, MP3 simple, not automatically leveled.
I think it's
okay.
PTW. It's PTW.
It's like a PTW. Okay, so in IPA we have noticed some issues. Maybe if anyone has an experience, you can comment on it. So when you change the field size, you have to change your reference, and then when you change your reference position, so you have to do the normalization again, and then you get your data. You measure your PTDs profile.
Sir, we don't have such type of issue.
Okay, so if anyone has IVA?
So we had an issue with the phantom because when a system open at the center, so engineer installed the other rods and the accessories, but somehow they put it in the vertical shaft in a wrong way.
Okay.
So what happens when we go down from the shallow to the deeper depths, our symmetry gets out more than 2%. So we
Okay.
acquired the beam data twice.
Oh my goodness. That's insane.
So that's why I mention a slide that we need to cross check if somebody is new like us, that your symmetry should be considered at the shallow depths and the deeper depths.
Yeah, that's
If
true.
it is
That's
not
true.
if it is not coinciding in the beginning, so it means you must need to check first your setup, then your machine. So it will save your extra labor.
Yeah, that's true. That's true.
ما كان مش عندي نت شكله قرب يخلص.
We have another question from Muhammad Abu Bakr.
Yes, I read that. ASCII is the only way to download calculation up to our TPS, depending upon the system you are having. But in our system, what we have right now, they required in the ASCII format. So system, the software, the dosimetric software automatically converted into the ASCII format. We just need to give a command and it will be converted. I guess so. There would be more validation and verification of the IMRT fields on VMAT if somebody wants to start the IMRT, because there will be a small beamlets and requires a specialized dosimetry, and you need to follow the specific documents as Sir Talat has mentioned.
Is there anybody have another question?
Just a quick question from my side is have you done electron commissioning for Monte Carlo electrons?
So
for electron, which algorithm you are using it?
Yes, sir. We are using Electron. What have written on the algorithm is EMC.
Yeah.
So it would be Electron Monte Carlo algorithm, and we took the data in wide open beam profiles and PDDs. Profiles was in air, and rest of the PDDs for applicators only.
Now, my question is not related to that. My question is related to the verification of the data, basically, because we actually have same issue here when we are actually using the EMC. We notice that when the body curvature of the patient is not flat, you feel the difference up to 10% in the manual calculation of your electron versus your planning data. So we are working on it. Actually, we have done some work, but is anyone has any notice such kind of issue?
Sir,
because especially when you're doing a breast.
I don't. We don't check this like curvy surfaces. But what I have noticed during because I have only checked the one reference plan data points now for the electron using Marcus chamber, but it is a great difference when you go to the periphery as compared to photons and electrons. It may be sometimes it exceeds more than 4.5% to 6%, 7%, and 8%.
Yeah, that's another issue with the EMC. It's pretty critical how you want to deal with that, actually, especially when the energies go smaller, the variation goes bigger. So if anyone has noticed such kind of issue with the electron Monte Carlo.
So somebody using can answer this.
Yeah. Is anyone in the group? Okay.
I think nobody is using EMC for calculation here in the group.
Okay, no problem.
Yeah. Another question from Mr. Kashif. Did you smooth the data
That's important. That's a good
Yeah.
question. So first was my approach was not to smooth that data because what have we actually we need to incorporate it. But at smaller fields, we used a one-step smoothing just only on smaller fields, not for field size above 5 by 5. Hello?
Yeah, I think these are all the questions. And to finalize this, I'd like to thank Faisal for your time and
I
for
would
your efforts.
I would like to make I would like to say something. If anybody finds anything a bit suspicious, or maybe I can say any mistake we did it to the during the acquisition, you kindly correct us, because that suggestion will also help us to improve our system, because we were new and it was a first clinic in our center and that was the first commissioning I performed, so I might be somewhere a bit confused. So if anybody finds anything that can improve our system data, our system configuration and the dose output, you can suggest me.
My recommendation is it would be great if you can ask someone from other center who has a similar setup. They can come down and have a the audit. Like when we have actually done in Shifa International Hospital, we asked the Aga Khan University Hospital. There was a Dr. Sher Ali. He was very kind to us. He came down for 2.5 days, 3 days. He spent with us. He checked over all the data. He did his own independent test on multiple things. He did end-to-end tests, and it was really helpful. And this is very common practice in Australia, that whenever we set up new things, we ask the request to the other centers. They will come down and do the audit for there are different level of audits. There level 1, level 1B, and so level 2 and level 3. So depend what you want. So it will be good if someone can do for you. That will be
No, sir,
very.
I will inshallah ask for this, because Kiran has the same setup, same machine.
Oh,
So
lovely.
they can also. Sir, I want to have an opinion from you.
Yeah.
I was making few plans using optimizer for the IMRT for the random check. No? I have exposed the Octavius 4D Phantom. But I'm having an issue that when I'm delivering all the fields at 0 degree, I'm having a 3 by 3 criteria by 97%, 98%. But when I'm giving them in rotating entry, it falls to 75 or 78%.
Yeah. So it's have you incorporating your couch?
Yes, sir. I am incorporating the couch.
Okay. So
But
have you?
when I changes the criteria from 3 to 5 for moving entry, it covers the 96%, 97%.
But it's too
perfect.
big. It's not recommended. Basically, according to the recommendation, there should be 3 by 3 millimeter, but 3% 2 millimeter is the
Yes, sir.
criteria for gamma analysis.
Yes, sir. So,
And
sir,
it's a global gamma.
exactly.
Not the, yeah, just make sure that you are using the global gamma, not the local gamma. That's another issue. You should be checking your Octavius that whatever you're using it. And secondly, the threshold should be approximately 10%.
Okay.
So this is another thing you have to be check in your system.
So it means, sir, I need to check this in the very soft.
Whatever the Octavius software is.
Okay. So the rest of the whatever we used to we use plans to verify on Activius, we use in the local gamma.
No. It should be global gamma.
Okay.
Okay. Local gamma is quite complicated. It's not easy to handle it actually, and it's yeah. There's a lot of issues.
Because when I had this variation, so I was thinking that whether something's wrong with the data in the system or something is with the Octavius.
Okay. One more thing, actually, when you doing this one, you have to make sure you have to adjust your DLG for this model, for specifically for IMRT, to make it
Okay.
work. Because sometime what happened, this is we have actually multiple machines, so we have a slightly different DLG value for different machines. So we have actually come to the consensus. We try to adjust the DLG to match in a way that all the machine can be incorporated. That if you are treating patient on one machine, could be treated on the other machine as well.
Okay.
So this is another thing we are doing it actually. So
Okay.
we have adjusted the reading which we get it is not we put it into the TPS. We adjust it, we change it, we rerun the system, and then we calculate it again multiple times, and then yeah, it was a nightmare basically.
So it means it's a similarly like we are matching the 100 MUs per 1 gray.
Now this is basically the simple. The other thing actually, you're using the Monte Carlo, the Akoros. If you're using Akoros, you know you reporting dose to medium, not dose to water.
Yes, sir.
So that's another issue, because if you're doing a dose to water at 10 centimeter, it will be different than the dose to medium.
Exactly.
So it is around 1% difference. Your
Exactly.
100 MU is not giving you the 100 centigrade actually. So that's you have to be incorporate in your system as well.
So we will check inshallah, and we will have a guidance of you from
Anytime.
inshallah.
No problem.
Inshallah. Thank you so much, sir, for
And
your time.
other recommendation is there is a Akil Hussain from Queensland. He has the same
Ji.
setup, so you can talk to him. I can send you his email ID. If you can text me on the group, you can privately message me. Then I will tell you his number and contact details.
Inshallah, sir. Inshallah.
Okay.
Thank you so much, sir.
No worries.
Thank you, Faisal, and thank you, Sir Talat, for your kind comments and discussion. I thanks all the participants for listening this one, and please stay with the MPTF for another lecture. We will update soon the details. Thank you all.
Thank you, sir.
Thank you very much.